T-minus 10, 9, 8,
The clock is 7. Operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8,
The clock is
7.
operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8,
The clock is
7.
operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8,
The clock is
7.
operating. We're underway.
Tranquility Base here.
Endeavor, go.
A gravitational wave is a propagating gravitational field. It's a ripple in space-time. Gravitational waves are predicted by all relativistic theories of gravity, although with slightly different properties. And they manifest themselves as changing the distance between separated test masses as the wave goes by, and also the rates at which separated clocks keep time. The Cassini gravitational wave experiment is searching for low-frequency gravitational waves by looking at the relative velocity between the Earth and Cassini. And the way we do that is the NASA Deep Space Network transmits an extremely precise microwave signal up to Cassini spacecraft. The Cassini spacecraft retransmits it to the Earth, and on the ground we compare the transmitted frequency with the received frequency. The difference between those two is the so-called Doppler shift, which allows us to measure the velocity between the Earth and Cassini. And if a gravitational wave is incident on the Earth-Cassini system, it shakes the Earth and it shakes Cassini in such a way that the Doppler time series, this time series of Doppler shift, has a characteristic 3-pulse perturbation in it, and that signature is what we're looking for. To get gravitational waves at potentially detectable levels, you need to have an extremely massive source. A black hole, binary black hole, for example, might be an excellent example. We're sensitive in the Cassini experiment for low-frequency waves, periods of about 1,000 seconds. And the best sources in that band for our experiment are massive black holes, about 100,000 solar masses or maybe 1 million solar masses. There are two reasons why gravitational waves are interesting. The first is as a test of fundamental physical law. These waves are predicted by all relativistic theories of gravity and really have to exist. And if they don't get observed with the properties, then we have a problem in terms of the physics. More interestingly, I think, is the fact that we have the opportunity here to do gravitational wave astronomy, to open up a new window on the universe. The gravitational waves will allow us to look into the deep interiors of these high gravity, high velocity regions that are generating the waves, and we'll get information that is really unavailable with lighter radio waves. The Cassini experiment is going to have exquisite sensitivity, the best sensitivity so far. And there are two principal technical innovations that are driving this. The first is that the Deep Space Network will be transmitting for the first time so-called Ka band, which is a high radio frequency with wavelength of about 1 centimeter. This minimizes some of our noises, plasma scintillation noise in the solar wind, for example. So that's one big improvement. The other big improvement is that we have a so-called advanced media calibration system out at the Goldstone station. This is a microwave radiometer which allows us to independently measure the fluctuations in the Earth's troposphere and correct those effects also. The Cassini gravitational wave experiment is going to consist of 3 40-day tracking intervals. The first one is between November 26, 2001 to January 5, 2002, and there'll be subsequent 40-day intervals 1 year after each of these. During this time, of course, Cassini is in free cruise between the orbit of Jupiter and the orbit of Saturn. And this experiment will happen before Cassini gets to Saturn, which of course is its primary objective and is independent of the Saturn science, which will be done starting, I believe, in 2004.